All right, so here's a video that talks about how to use z-scores and how we assess normality. So in the previous lesson, we learned how to calculate z-scores, and we talked about what a z-score actually means. We learned that it is the number of standard deviations someone is above or below the mean. So in this particular problem, we're looking at two characteristics, speed and strength. And we have a player here that says that they can run a 40-yard dash in 4.2 seconds and can lift 370 pounds. So in this case, we're going to find the z-score for both of these different things. So in terms of time to run 40 yards, remember the way we calculate our z-score is we take our data value, which is 4.2, minus the mean, which is 4.6, divided by the standard deviation, which is 0.15. So I'm just going to pull up a calculator here. So 4.2 minus 4.6 divided by 0.15. So that's negative we'll say to negative 2.67. So remember, in this context, since we're talking about speed and the amount of time it takes to run, this is actually good. This person is fast, right? They're below average, I guess, in terms of speed. But since it's measured in time, we think that that's good. That's about 2.2 standard deviations below the mean. And then to calculate the z-score for the amount of weight lifted, it's going to be 370 pounds minus 310 divided by the standard deviation, which is 25. So 370 minus 310 divided by 25, that gives me a standard deviation of 2.4. So interpreting these in context, it means that this player is fast. He's 2.67 standard deviations below the mean in terms of time it takes to run 40 yards. And in terms of strength, he is 2.4 standard deviations above the mean. In this case, that's good. So this is a good player because he is, I guess you can say, above average in both the amount of time it takes him to run as well as the amount of weight lifted. Okay, so now we're going to go a little bit further with our understanding here. Now let's talk about what if instead we wanted to answer this in something that's a little bit more, that people would understand a little bit more in terms of common language, right? Because if we said z-scores or standard deviations, the average person wouldn't understand what that meant. However, if you ask yourself the question, what percentage of players are faster than this player, and you said that, then that would be pretty reasonable to understand. And if we said what percentage of players are stronger than this player, again, that is a statistic, or that is something that someone would understand. So if we just think about what this looks like, right? So we did our z-score calculation. We found in terms of time to run 40 yards, he was 2.67 standard deviations below the mean. So maybe somewhere around here. And if we want to know what percentage of players are faster than this player, well, the only people who are faster than him are people who had smaller times. So that would be this case. So this amount of people are faster than this player. And then if we think of in terms of amount weight lifted, right, we found that z-score to be 2.4, which we know if this is the mean, he was about 2.5 standard deviations above the mean, which means that this amount of people are the only people who are stronger than him. So what we're going to learn today is actually how to find that area so we can determine what percentage of players are faster and what percentage of players are stronger, which is going to further indicate that this player is a good player. Okay, so now let's talk about what we're going to use to find those percentages. To find those percentages, we're going to use something called the standard normal distribution. So this is basically a standardized version of it's a distribution of all of our z-scores. Okay, our standard normal distribution has a mean, the center is 0, and every standard deviation is equal to 1. Okay, so if we look at the standard normal distribution, we have our z-scores on the bottom. We have our mean in the center, which would be, as we learned yesterday, a z-score of 0 would mean that you're equal to the mean. Okay, and what you might have learned in Math 3 is that about 68% of observations fall within 1 standard deviation of the mean. 95% of observations fall within 2 standard deviations of the mean, and then about 99% of observations fall within 3 standard deviations of the mean. So this is something that we did yesterday, but we can actually take our standard normal distribution, we can actually put our real world values in there if it's given to us in a problem. So this is the information we learned yesterday. The average 9-month-old baby weighs 19.6 pounds with a standard deviation of 2.45 pounds. A lot of us remember that we can actually put those weights in our distribution, right? So if our average is 19.6, we can put that in the middle. And then to go 1 standard deviation above the mean, we're going to add the 2.45. So I'm going to go to my calculator here. So 19.6 plus 2.45. So that would give me the weight 1 standard deviation above. And we can actually just keep adding 2.45. That's going to give me 2 standard deviations. So 2 standard deviations above the mean would be 24.5. And then 3 standard deviations would be 26.95. So we can fill out those values here. So 1 standard deviation was 22.05 pounds. 2 standard deviations was 24.5 pounds. And then 3 standard deviations was 26.95 pounds. All right, and then we can get the same thing on the other end, but instead we're actually going to subtract. So 1 standard deviation below would be 17.15. 2 standard deviations below would be 14.7. And then 3 standard deviations below the mean would get me at 12.25. So we can fill in those real world values here as well. So 1 standard deviation below was 17.15. 2 standard deviations below was 14.7. And then 3 standard deviations below was 12.25. Right, and all of these are pounds. So then what we saw yesterday is we can place an individual here. So if you remember the example, I said that my son was 24.6 pounds, right, which would put us just above 2 standard deviations above the mean. And then what we're going to learn today is how to find the probability in terms of where he lies in relation to everyone else. So that's how we filled out the real world values using our standard normal distribution. Okay, but in order to use z-scores, we have to make sure that our data is normally distributed. So what I mean by that, because our standard normal distribution is, again, normally distributed, symmetric, it's a bell curve, our data has to also be normally distributed. How can we tell if it's normal? We have to check what's called the normal probability plot. Sometimes it's called a normal quantile plot. And then we have to determine if it looks linear. If it looks linear, then we can determine that, yes, the data are normally distributed. So an important thing to realize that even if a histogram or stem plot looks roughly symmetric, if the normal probability plot is clearly not linear, we can't conclude that the distribution is normally distributed. So we're always going to rely on this particular plot to determine if our data is normally distributed. So just so we have an understanding about what a normally distributed or normal probability plot looks like and how it's constructed. Essentially what we do to construct them, and you're not going to have to do this by hand, we're going to use technology. You're going to arrange the observations from smallest to largest, and we're going to record each percentile the data occupies. Then you use the standard normal distribution to find z-scores at these percentiles, and then you're going to plot each data point against its corresponding z-score. If the points fall close to a linear pattern, the data are normal. So again, you don't have to worry about that. What you need to worry about is just being able to read the plot. Okay, so what do they look like? So here's what a normal probability plot looks like. It's these things at the bottom that kind of look like scatter plots. So if our data is skewed right, our normal probability plot is going to have kind of like a curve, almost like an exponential function a little bit. Okay. If our data is normally distributed, we can see that our points fall roughly in a linear pattern. And if our distribution is skewed left, it's going to be curved, but in the other direction. So what we're looking for here for normally distributed is in this middle. This is what we want our normal probability plot to look like. All right, so let's make a normal probability plot in GeoGebra. So if we click on this data gives the unemployment rates for the 50 states. So our observational unit is the states, and then the data that we're collecting is the unemployment rate. So we're going to collect this data. This data happens to be a range from smallest to biggest, but it doesn't need to, remember, when we put it in GeoGebra. And now I'm going to paste this data into GeoGebra. Okay, we're going to highlight and we're going to do one variable analysis. So we make a histogram, but remember that's not the plot that we're going to look like to determine if it's normally distributed. Instead, we're going to look at the normal quantile plot. So as we can see here, since our points roughly follow a linear pattern, we can conclude that this data is normally distributed, which means it is appropriate to use z-score calculations for this type of data. Okay, so now let's go back to our problem here. So it says we calculated the z-scores for these individuals, and if I look back at my calculator, we have our z-scores for the time to run. It was z equals negative 2.66, right? And then for strength, it was 2.4. Okay, in this problem, we want to figure out what percentage of players are faster than this player. Okay, so we sketched a little distribution here, right? And we determined that, if our mean is at, well, we can use our standard normal distribution now that we've converted it to a z-score. We know that this is where 0 is, so negative 2.66 is going to be somewhere to the left here. And if we want to know what percentage of players are faster, the faster players are going to be in this area of the distribution because they're going to run a time in a time faster, less seconds than this player. So we want to figure out what this area is. And then if we're talking strength, right, now that we've standardized our data value, we can use our standard normal distribution where the mean is 0. 2.4 is somewhere to the right of 0. And if we want to know what percentage of players are stronger than this player, we would be looking for this area. We're going to use, so what you learned in Math 3 is using a z-score table, but we're going to use technology in this class to figure this out, okay? So actually, it's going to be in GeoGebra. And what we're going to do is we want to open so let me actually start fresh with GeoGebra. We're going to open the probability calculator. So to get that open, you can click on the 3 lines, the 3 dots, and click on probability calculator. So this is going to open a calculator that's going to calculate that percentage for us. And what's nice about this is it kind of sketches our distribution. So we know that this is the area that we want. So these values tell you that that's the area to the left. So to get the area to the left, we're going to click on the leftmost button. If we wanted the area to the right, we're going to click on the rightmost button. If we want the area between two numbers, we're going to click on this one. Okay, so since we want the area to the left, this is what we're looking for. Okay, but we want the area to the left of this z-score, negative 2.66. So I'm going to type in negative 2.66, and this is our area. So it's telling me, this problem is telling me, or this calculator is telling me that this area to the left, which I sketched here, is 0.0039. 0.0039. Okay, the other thing we need to understand is that total area underneath the curve is equal to 1. So that means that if we wanted to think in terms of percent, we move the decimal over, multiply by 100, that's 0.39% of players. So only 0.39% of players are faster than this player. If we're looking for the area to the right, we can use the same calculator. Since we're looking for the area to the right, we need to make sure we select the area to the right. And we're looking to the right of this z-score of 2.4. So I'm going to change this to 2.4. There's the area, matches our sketch here, and that area is going to be 0.0082. So this area right here is 0.0082. And as a percentage, that's going to be 0.82%. So less than 1% of players are stronger than this particular player. So to answer this question, what percentage of players are faster than this player? That's 0.39% of players are faster. And what percentage of players are stronger than this player? That's going to be 0.82%. So just to kind of revisit this, the reason why we shaded the area to the left is because if you are faster than the player, you have smaller time. So that's why we shaded to the left. In this case, we shaded to the right because we're looking for what percentage of players are stronger than this player. If you are stronger, you're lifting more pounds. So that's the area to the right. The total area under the curve is equal to 1. And this represents the proportion of the area, 0.0082, which you can convert to a percent by multiplying by 100. Okay, so let's continue looking at some examples in terms of finding area. So remember this example that we did yesterday. So we had this example where we had my son Archer and his weight, and then we had my friend and her weight. And yet, in the previous lesson, we learned how to find what the z-scores were for these particular individuals, and then we determined which player, or which baby was bigger. So just to kind of revisit, to do that z-score calculation, so this is for the boy. To do that z-score calculation, we did 24.6 minus 19.6 divided by 2.45. And then for the girl, we did 23.1 minus 18.1 divided by 2.33. And if you remember, this z-score was 2.04, and this one was 2.15. So we determined that the girl weighs more relative to her distribution because she's 2.15 standard deviations above the mean, whereas the boy is about 2 standard deviations above the mean. So usually when you bring a baby to the doctor, they actually report their weight in terms of percentiles. So what we're going to learn how to do is how to convert this number now to a percentile. So first we need to make sure we know what a percentile actually is. So a percentile represents the percentage of individuals that are at or below a certain value in a sample. We round to the nearest whole percent. So for example, if you take the SATs, a lot of times they report your score as a percentile. They say if your score is in the 80th percentile, that means that 80% of scores are at or below your score. So below means to the left. So that's what we talk about when we talk about percentiles. So let's go back to our example here. So just remember for Archer, our z-score was 2.04. And then for baby girl, our z-score was 2.14. So again, we're going to sketch our distribution here, right? Now that we've standardized our score, we can use our standard normal distribution. 2.04 is somewhere up here. And since we're looking for percentile, that means the area to the left. So we're shading, this is the area that we want to find. Same thing for the baby girl, right? We've standardized our score so we can use a standard normal distribution. 2.14 is somewhere up here. And since we're looking for percentile, we're shading the area to the left. All right, so now we're going to pull up our calculator. Right, we want the area to the left, so we're going to select this, and then we're going to type in 2.04. So percentile in this case for the baby boy is going to be, if we want to convert this to a percent, so that's 97.9%, but we convert to the nearest whole percent, so that's going to be the 98th percentile. And then we're going to do the same thing for the baby girl, but this is 2.14. We're still looking to the left because it's percentile, so that's 0.9838. So that's actually also going to be the 98th percentile. Hold on. 2.04. Yeah, so 97.93, that's slightly lower. That's 98th percentile. So they actually are both in the 98th percentile. However, we saw once we rounded it that the baby girl Archer was around like 97 point something, where this is 98 point something. So this is also the 98th percentile. So in all reality, when it comes down to it, even though this is 2.14 standard deviations above the mean, if we're talking percentiles, they're roughly the same. But if we want to be super precise, we would say the girl is heavier in terms of relative to her distribution. Okay, so just so we make sure we know how to find some basic, just finding the probability using the calculator. So there's a couple things that we need to know in order to find these probabilities. We just need to figure out, we need to know what the z-score is. That's what we're going to type in. And then less than is going to tell me whether I'm going to the left or to the right. So since less than, that means that we're going to go to the left. So going to my calculator, we've already have less than. I'm going to type in 2.5. So that probability is 0.9938. So that's going to be B. So sometimes it might be written in this notation, which is basically saying find the probability that z is greater than negative 1.23. So greater than means to the right. So that means we're looking, if we wanted to kind of draw a picture of what that looks like, right? Negative 1.3, if this is 0, negative 1.23 is down here. Greater than means to the right. This is visually what we're looking for. So I'm going to type in, well, first of all, I'm going to switch to greater than. So we're looking for the area to the right. And then I'm going to type in negative 1.23. That matches our picture. That proportion, that probability is 0.8907. Oops. As we just learned, percentile means less than. So z-score of 2.06. So less than, I'm going to switch to less than. I'm going to type in 2.06. So that's 0.9803. So the 98th percentile here. And then we can also use this chart to find, or not this chart, this calculator to find areas between. So visually what that looks like. All right, so we have our standard normal distribution. Our mean is 0. Negative 0.04 is like here. And then 2.13 is right here. So when we're looking for between, we're looking for this area right here. So going to our chart, the between is going to be this one right here. As we can see, it shades between. Just so you know, this one is if we wanted the area to the left and to the right. We won't really see that as much. This is the area between. So we're going to type in the smaller one here, so negative 0.04. And then we're going to type in the bigger one here, which is 2.13. So the area between those is going to be 0.4994. So that's going to be D. Okay. So now let's just take a look. I'm not going to do all of the examples that we did in class. However, I'm just going to do one. So for each of these problems, you're going to sketch a picture of the distribution with the real world values, just like we did at the very beginning part of the lesson. Then we're going to shade part of the distribution that we're looking for. We're going to find the z-score, and then we're going to find the proportion, percent, or percentile, depending on what it asks for. And then we're going to answer in context. Okay, so let's just take a look at this one. So suppose that SAT scores among U.S. college students are normally distributed with a mean of 500 and a standard deviation of 100. So first thing we're going to do is we're going to sketch a distribution with real world values, okay? So here's my distribution, right? Our mean in this case is 500. And we're going to find the numbers 1, 2, and 3 standard deviations above and below. So luckily this is pretty easy since our standard deviation is 100. So 1 standard deviation above would be 600. 2 would be 700, and 3 would be 800. And we're going to do the same thing below. This is 400, 300, 200. Okay, and it probably is helpful to choose a different color here. So it says, what is the percentile for an individual who has an SAT score of 600? So we're basically looking for this area right here. So here's 600, right? But it's asking for percentile. So percentile means the area to the left, which means we're going to be shading this area. Okay, so that's what we're looking for. So now we're going to go ahead and do our z-score calculation. Well, I already know it's one standard deviation, but z-score calculation, we're going to take our data value, which is 600, minus our mean, which is 500, divided by my standard deviation, which is 100. So that gives me a z-score of 1. So I know that this individual is 1 standard deviation above the mean, but in this case, since we're asking for percentile, we want to figure out that area to the left. Okay, so using our notation, it's basically probability that z is less than 1. And we're going to go ahead and put that in our calculator. So since we are looking for less than, we know we need to choose the less than part. And we're looking for our z-score of 1. In that case, it's going to be 0.8413. So percentile, we round to the nearest hundredth. So that as a percent is 84.13, which means that we are in the 84th percentile. So to answer in context, we're going to say an individual who scored 600 on the SAT is in the 84th percentile.